Good morning, good afternoon, good evening, wherever you are. Welcome to another Nvidia and ArangoDB webinar, hopefully the first of many, actually. My name is Corey Summers. I am the Chief Marketing Officer for ArangoDB. And joining us from Nvidia, Brad Reese and Rick Ratzel. And also on the ArangoDB side, Anthony Mahana, who will be giving us a wonderful live demo this morning of the integration that we're going to share with you today. So let's get started. In terms of an agenda today, we are going to, first of all, give you some background on how this all started. And we'll be hearing from the NVIDIA folks on, thoughts on how this began and why Arango was the right selection for this. We'll look at some of the NetworkX challenges and perspectives on why this is needed. I'll give you a little background on ArangoDB for those of you who don't know much about us. We'll look at the design approach and guiding principles. So kind of how did we go about doing this the way we did? We'll do that in-depth demo that Anthony will showcase for you, really exciting. It'll be a technical demo, so get ready for that. If you are technical, you will be, I hope, very happy with what we are going to show you. We would like you to provide your questions as we go, and if we can, we will field them as we go. And if we don't get to them, we will get to them at the end. Also, if there are things you're seeing that spark your interest or you might think would be a good next step for this integration or something that you'd like to see added, we would like you to share that as well as we go, or at the end, we will have time for that. All right, let's get into it. Let's start with kind of the conception of this, and for that, I'm going to turn to Anthony to give us a little bit of overview.
Yeah, sure. So just at a high level, what we're currently looking at is a diagram of how NetworkX users currently work with their graphs in memory in Python. Just recently, there's this concept of a NetworkX QGraph backend that has been added, allowing you to dispatch traditional CPU algorithms to GPU for significant performance increase. Now, where the trouble that we're seeing now from just this diagram alone is that the condition that these graphs are in memory remains. And so what we want to propose is the next slide, which is where we see a tighter integration with ArangoDB, allowing you to maintain and persist your NetworkX graphs, all while still being able to benefit from the GPU acceleration that NVIDIA is providing. So it's a symbiotic relationship between NVIDIA, NetworkX, and ArangoDB. And we'll talk more about it a bit later. But for now, I'll hand it off to Brad, who will talk more about QGraph and NVIDIA.
So I wanted to kind of jump back into time some. So NVIDIA, we are building libraries that others use to make their products better. So we are actually building a graph engine, except for customers approach us and they are like, hey, can you do, graph queries and Tinkerpop? You pick your favorite language. And we keep saying, no, all we do is graph algorithms. And so years ago, I realized that needed to partner with, a graph database really to build kind of a cohesive solution that helps the ecosystem. I was at a conference, I can't remember how many years ago, and I ran into folks from ArangoDB. We had a nice chat, and the Arango view on performance, scalability, and kind of the graph community as a whole really gelled with what NVIDIA was doing and our view of the environment. So we've formed this partnership. It has been wonderful. We've been doing it for 4 years now. So things are working and we keep adding more things and trying to make graph users' life better. So next slide. So a quick flashback to the product. QGraph was launched back in 2018 as part of our Rapids endeavor to kind of accelerate all of data science. We have a growing list of algorithms. All of our algorithms, we work to become scalable and hopefully the fastest version of the algorithm out there. We've scaled PageRank up to 4.4 trillion edges. We get pretty good performance, even though we see these numbers and we keep trying to make them better. Louvain clustering, I think this is the largest, attempt at clustering of Louvain. We did 1.1 trillion edges. Recently, we did a test using our GNN tools on 1.6 trillion edges. So we like things that scale, but it goes from very small graphs all the way up to whatever size you need. So looking across the libraries, across the top and then our stack below, going from left to right as far as complexity, we have our libcugraph, which reaches down into our C and C++ libraries. This is really for users that understand graph, because you have to define the graph structures that you give us. There are no guardrails. If you give us bad data, we'll just crash. On top of that, we have a very thin, lightweight Python wrapper that we call PyLibcugraph. This is really an integration layer that we have out there for not only our own code, but other people to use. So you can pass in CUDA arrays, CuPy arrays, NumPy arrays, but you still have to understand graph and what the arrays mean. At the far right, then we have cugraph, which is our top level, very, I would say, fat package. It has tons of guardrails, convenience functions. If you specify your graph in strings, we'll do automatic conversion and renumbering for you. We'll tell you if the data is correct or not. When you add all these safety guardrails, though, it does slow things down and makes the package larger, but it is a very nice entry point. cugraph is then built on top of our other stuff. What we're announcing today is really our network integration piece called NX-cugraph. That ties into PyLibcugraph, and it's really code to handle the translation between NetworkX and our code, and that's where NetworkX reaches in. At this point, I'm going to turn it over to Rick and see if there's any questions.
Yeah, we do have one question. Can we apply traditional graph methods like graph traversal using BFS, depth first search to find all child nodes other than the graph analytics algorithms?
So, we just do standard graph algorithms like BFS and traversals.
Yeah, we have those algorithms in our library already.
Great.
There is an option later that we're working on to expose more of the high performant graph primitives so that you can write your own graph algorithms using those that sit on top of the C and C++ CUDA libraries. I don't think those are ready yet, but those are planned.
And we're kind of expanding all of our traversal algorithms, start doing more all pairs and multi-seed stuff. And if there's ones out there that you really need, let us know. Take it away, Rick.
All right. Thanks, Brad. Yeah, Brad explained the cugraph libraries that are part of the cugraph package project. This sort of explains it a different way Nvidia's approach to the whole thing and how they've described the evolution of accelerated computing. As you're aware, the whole experience isn't just about hardware and Nvidia GPUs, but it's also the software that enables those. So, starting at the bottom, people are probably familiar with CUDA. It's been around for a while. This has enabled people familiar with C and C++ concepts to easily leverage the GPU. But moving up the stack, you can see that we've built C and C++ CUDA libraries that sit on top of raw CUDA kernels. These are more application specific for the C and C++ user. Convenience-wise, we've extended that even further and encroached into Python. So Python CUDA libraries are also available. You can work with CuPy arrays and Numba, Python wrappers for just various CUDA kernels are there. Further up is the Rapids project. So the philosophy here is that you're using data science libraries that you're familiar with and you don't necessarily want to leave. You have these options with Rapids to use high-level Python libraries like cugraph that are very similar to what you're already using. Recently, though, we've extended it even further. You don't have to change any code. You just enable the software and have a GPU available And at the very top there, you can see zero code change acceleration plugins. That's what we're going to talk about today, NX cuGraph in particular. The Rapids project, though, also has accelerated pandas, the same idea. Zero code change, pandas code accelerated with the GPU. So now if you, there we go. So mapping this back to what Brad presented, if you're a C++ user, you can use libcugraph. We also have a C API in that library that will enable our C and C++ performance graph analytics libraries written in CUDA to empower your C++ project. If you're a Python user and you have you want a tight integration with performance almost on par with libcugraph, you can use pylibcugraph. Like Brad mentioned, you have to be pretty familiar with graph concepts, but you will have basically all the power of libcugraph in Python. Further up the stack, cuGraph, the high-level graph library for convenience, very similar to NetworkX. And then NX cuGraph, which we're going to talk about in a minute. That is just, if you know NetworkX, you're pretty much done. Turn on NX cuGraph and have a GPU and you go much faster. So NX cuGraph, a new project here. This is enabled, this is a NetworkX backend. Backends are relatively new to NetworkX as well, starting in version 3.0. Backends aren't exclusive to any Nvidia project. There's other backends. Nvidia's, Anthony's going to talk about his, of course. But you can see in that, flow there that the black boxes being those common to all NetworkX backends. The purple one is NX cuGraph. It fits in just like any others. You don't have to learn any new APIs if you're a NetworkX user. You just turn on NX cuGraph and it will do all the conversions to GPU, run the function on the GPU, return the results as you're familiar with. Multiple backends can be used together. This is where the interop between NX ArangoDB, the Arango backend for NetworkX, and the cuGraph backend work together. Anthony, like I said, is going to talk about that quite a bit. So how does this map to what a user sees? Well, it's pretty straightforward. You know NetworkX and that code in the top, that's something you can type in right now after installing NetworkX and NX cuGraph. That will work today as is, and it will run between the centrality on that data set. If you simply enable the cuGraph backend, like on the second line, you'll get a significant speed up. So here without the backend, this particular between a centrality run on this graph takes almost 8 minutes. You turn on NX cuGraph, the exact same code runs in 20 seconds. I think our latest version we're about to release will result in about 5 seconds total. So we do have an improvement coming up. But between a centrality, as you know, that's you know, an approximation algorithm that uses a certain fixed number of shortest paths to find the between centrality scores. If you increase that number with that K value, you can see just how much speed up you can get. Of course, the higher the number, the better, more accurate results. And this is where GPUs really shine, because the parallelism allows us to scale to, you know, high values of K without much impact at all, resulting in this, in the case of this workstation I was on, over 600x speed up.
So there's a very good question, which actually the answer really hinges on what Anthony's going to talk about. The question is, how do you handle the frequent updates to the graph? Graphs are stored in memory. For example, as you know, you have millions of users and relationships coming in every minute.
Yeah. A lot of these workflows are based on reading data from a disk, the graph is fixed, or I don't want to spoil it, or reading it from ArangoDB, and then transferring that to GPU, running the algorithm. That data transfer is, in some cases, more expensive than the algorithm itself when it's run on GPU. So there is a transfer penalty there in conversion. The NetworkX dispatching feature, though, does have graph conversion caching built in, so that you only pay that penalty once if you update the graph. So yeah, if you update the graph frequently in a loop, you're adding edges incrementally. The first time you call an algorithm after those updates, you'll see that conversion penalty. All subsequent calls, if there's no updates, you won't. But yeah, that's a great question. That does happen.
But this ties into what Anthony's going to talk about of why you want to use a graph database if you have updates coming in this frequently. The other question was, will the user benefit from this platforms?
Yeah, we've seen great benefits so far. I mean, these results alone have allowed people to work in ways that they couldn't before in NetworkX. Basically, there's a workflow that reads in all of the Wikipedia data as a graph and performs various analysis on it using PageRank. For non-accelerated, that run takes, just the PageRank run takes about 50 minutes on the workstation I was using. With NX cuGraph enabled, it was in the order of 20 seconds, I think. So once that happens, it sort of unlocks a lot of exploration you can do with that data that you couldn't do before. So those are typical benefits that users see. And again, it's zero code change. So the investment that they have in their workflow has already been paid when they write the familiar NetworkX code that they prefer to use. So it's a very easy transition to GPU using these backends.
And this is a question to the NVIDIA folks or Anthony, if you're thinking about a production application that you want to roll out to potentially hundreds or thousands of users, what are the differences between doing that somehow in NetworkX in memory versus persisting to ArangoDB? I suspect that it's going to be a lot better or easier to do that once it persists if you have 1,000 users or more to an application.
Yeah, I mean, I can answer first. Just the confidence of being able to say that your data is persisted somewhere so that you don't have to worry about data write or data pre-processing every time you start a new Python session is already a huge win, right? So previously, NetworkX users had to, live comfortably with the idea of losing their graph whenever that Python session terminates. But now, with ArangoDB as the backend, that's no longer an issue.
Great. All right. A little bit about Arango for those of you who don't know about us. We are one of the main leaders in the graph database market. Here you can see we had the privilege of being named by G2 as the well and away the most high satisfaction graph database there is. So one of the reasons for that is the scalability. So what you're able to do with ArangoDB that you can't maybe with other solutions is scale horizontally and in a transparent way. So imagine adding nodes to a cluster and not having to worry about restriping your data, worrying about data loss across those nodes. Everything is lights out in that sense. So that's just one of the reasons we've had that leadership position. And I suspect that as you persist data to Arango, you're going to want to leverage that scalability. Now, in terms of our overall architecture and offerings, we've got that multi-model graph database. That's the other benefit you're going to get is not just having that graph data persisted, but being able to add in document data, full text search capabilities, geospatial capabilities, key value, all on a single platform. So giving you the ability to consolidate. A lot of our customers are consolidating multiple databases onto this platform with the obvious benefits there. We're adding the graph ArangoDB Data Science Suite, which is very exciting, and certainly a tie-in here with the graph analytics piece being dramatically accelerated through cuGraph. But also, once you persist your data to Arango, and this is very important, it opens up your ability to apply GraphML. So in a very powerful predictive fashion, you can apply that to many use cases where you want to get ahead of the curve and predict things before they occur. And certainly the Gen AI piece that Anthony is going to show you, once you persist your data, you can open up your applications to natural language capabilities in a very rapid fashion. In fact, this is kind of the way we're doing that through LangChain, our LangChain integration pack, which very rapidly allows you to add that natural language component either through a public or a private LLM implementation within your environment, certainly for security reasons. So this is really exciting just because the speed in which you can do this, and of course the benefits of GraphRag are coming into play here. So you're able to get a lot more contextual answers relevant answers, more cost predictive in terms of how that LLM is used versus other approaches. So this is a real benefit there. And this again is what we see our customers doing is adding a chatbot to existing applications to make them more competitive and upgrade their capabilities. So with that, I'm going to stop sharing. I'm going to hand over to Anthony, who will continue with a few slides and then the demo. So we've got about 5 minutes, Anthony, to go through these next set of slides, and then we'll get into the demo. And there was another question on recommendation systems. This is one of the core use cases for ArangoDB. So yes, you will be able to do that, and also in a predictive fashion. So we have customers who are using us to predict which recommendations are the right ones for various customers, even during an interaction. So we'll get more into that. Anthony, let's move forward on your side here.
Yeah, for sure. All right. So thanks, Corey. It's nice to go over this, because it brings more context to why we think ArangoDB is a perfect match for NetworkX and QGraph. So I'll take some time to give a general overview of the product, and then we'll do the demo. Right. So we're back to this image with a general understanding of what ArangoDB brings to the table. Previously speaking, NetworkX users typically had to undertake a complex set of operations for persisting graph data. This would include some kind of manual data import from flat files or some kind of database. And so simply starting a new Python session, like I previously mentioned, meant that you had to reinstantiate your NetworkX graph with some form of data loading every time. Of course, this comes with a unique set of features, and it forces you to spend effort on managing data rather than focusing on the benefits of just using NetworkX and QGraph. Adding ArangoDB as a persistence layer means that you'll be able to spend less time on data preprocessing and writing in favor of relying on our read capabilities to get your data into memory as fast as possible for when you want to run graph algorithms, whether that be on CPU or GPU. And so this integration is offered via a Python package called nx-ArangoDB. It's built upon the concepts of the backend, the concept that Rick previously introduced. So, which is why you'll often hear us refer to this product as the ArangoDB backend to NetworkX. And so, similar to what Rick mentioned, NetworkX utilizes a plugin dispatch architecture. So it means that you can redirect native function calls to backend implementations of that function. So instead of using NetworkX's pure Python dictionary implementation of graphs, we're able to create custom Python dictionaries that maintain a remote connection to your graph in ArangoDB, thereby establishing this concept of persistence. So at a glance, you can continue to use NetworkX graphs as you would normally, but with the added benefit of having your graph operations reflected in a DB. Things like cross-collaboration on a graph becomes possible. So if your graph is too large to fit into memory, but you and your team need to perform constant CRUD operations on it via NetworkX, then NX ArangoDB enables you to do that. Furthermore, having ArangoDB store your graphs also means that your DB can scale both horizontally and vertically. That's multiple nodes, allowing you to handle larger data sets. And so, like Corey mentioned as well, emphasis on inheriting ArangoDB's multi-model capabilities. This means that you can store more than just your graph data. So this would apply to document data, key value as well, all while being able to leverage the full text search and geospatial capabilities in Arango. And so from a data structure perspective, it's nice because, NetworkX graphs are built upon dictionaries of dictionaries of dictionaries. And so because ArangoDB is JSON native, we support the ability to store nested objects. And so similar to how you can, add nested objects for an ArangoDB, for a NetworkX node, you can have that same functionality reflected in ArangoDB. Okay, so just a quick hello world example for what this actually looks like. On the left-hand side, you see a traditional import statement from NetworkX, along with a new import statement for the ArangoDB backend. We also see some environment variable configuration to define the connection credentials of our ArangoDB deployment. So let's just assume that we're set up here with a graph that exists in the DB called mygraph. Instantiating a NetworkX ArangoDB graph is no different from instantiating a NetworkX graph, with the small exception of providing a name parameter, which will tell us which graph you want to connect to in DB. So let's assume that the graph already exists. Invoking algorithms on that graph is no different. You would just use the NX library and pick the algorithm that you'd like to use to and then pass that object. On the right-hand side, you'll see how this is done from a dispatching perspective. So the traditional PageRank API will dispatch the PageRank implementation to our backend. And our backend will then take the responsibility of pulling the data from ArangoDB if it already hasn't been done yet. Now, the decision to pull the data depends on whether you're running this algorithm on CPU or on GPU. So if you're running this on CPU, then you can fetch this as a NetworkX graph, which means the traditional node and adjacency dictionaries that you may be familiar with. If it's on GPU, then you can just rely on a COO representation, which is faster and much lighter when it comes to memory. So based on the representation you fetch, you can then dispatch to the algorithm associated to that representation. And then for now, of course, we only support either the default NetworkX backend, the default NetworkX implementation, or the QGraph implementation of that algorithm. But this is the first example of a NetworkX backend talking to another backend. So it's a really nice way of saying, this concept of being able to dispatch algorithms or dispatch function calls can talk to other backends as well. So from a CRUD perspective, this applies the same way. So NetworkX ArangoDB graphs are subclassing NetworkX graphs, which means that we inherit the functionality of traditional graphs. This applies to all 4 graph types. So graph, digraph, multigraph, and multi-digraph. CRUD operations are synced to the database. So adding nodes, updating edges, adding properties on certain nodes. Anything that you would see here, you can assume is going to be reflected in your DB. We'll see that in a demo in just a moment. The nice thing about these graph types is that from an ArangoDB perspective, you can use these graph types with the same data set. So we're not actually duplicating edges if you're transitioning from a directed to an undirected graphs in ArangoDB. We're just simply disregarding the edge direction. We can do that because we inherit a query language that allows us to disregard edge direction. So going back to that comment about if traditional graph methods are supported, the answer with this package is absolutely, because we're a graph database, you get to use these query language, you get to use these functionalities for doing traditional graph traversals. Okay, fast forward, what is the outcome? You get 2 winners here. On one hand, NetworkX gain a storage interface, and you get to inherit the query language, the visualization tools, and the question answering tools with LLMs. You get the confidence of persisting and reloading your data. And then on the right side, ArangoDB users suddenly inherit dozens of graph algorithms, and they can leverage GPU acceleration for significant performance. So I'm going to switch over. This is a different view now. What you're seeing here is the Arango Graph dashboard. Arango Graph is our managed service for ArangoDB that's available for cloud. And so I have a database running here, a pretty standard database. If you're wondering, this costs me about $2 an hour to run. So pretty standard in terms of what we have. We have a sharded deployment with 3 nodes, 16 gigs of memory for each node. So I've got a database spun up. I'm going to navigate to something called the Data Science tab, which is ArangoDB's Jupyter service-based offering for utilizing our data science suite. So next to every Arango Graph deployment, you have access to a managed Jupyter Lab service that you can use to work with your data in ArangoDB. So I've got 4 notebook servers here running. I'm going to click on one of them, which will take me to a Jupyter Lab server, and then I can get started with the demo. It takes me to an empty notebook file, which is perfect. It's what I want to use here. And just as a reference, I'm just going to quickly showcase the kind of hardware that we have access to right now. So I'm working on a Tesla T4 Jupyter Notebook server, and I've got CUDA 12.6 installed. Okay, now the first thing we'll do is I'm just going to bake the simple import statements that you saw in the Hello World example, just to showcase some of the functionality. Once we do have this imported, I'm going to create a specific database in my ArangoDB deployment. I'm going to call this database Karate. Just as a reference, in an Arango graph deployment, you can have multiple databases, and we're going to go check that out right now. So if I copy this password, open the database UI, for those using ArangoDB before, you might be familiar with this environment. See here that we now have a new database called Karate, and it's currently empty. So this will be the first part of the demo. We're going to use the famous Zachary's Club Karate dataset to basically showcase some basic CRUD on NetworkX ArangoDB. I just want to make sure that the font is not too small, so I'm just going to make this a bit bigger. Right, so I have a traditional NetworkX graph at my disposal, and the first thing I want to do is I want to get this ingested into ArangoDB. To do this, I would need a database connection. So in this case, I'm just going to say connect to the database Karate. And from here, I want you to instantiate a NetworkX ArangoDB graph, providing the name Karate, the incoming graph data parameter as the NetworkX graph. So this is no different from how you would normally do this, along with the DB connection. So from here, this is going to connect to the database. Now it looks like let me just quickly try this and use the Karate database instead. So I've loaded the data in here. If I get rid of this and go over here and hit refresh, I can now see my data persisted. I can also visualize that graph just really quickly, just to give you an idea. Very small graph with like 33 nodes. Great. Now I have a ArangoDB graph at my disposal. I can start doing things that I would normally be able to do in NetworkX, such as printing the, oops, looks like I misspelt it, such as printing the degree of my nodes. I can move forward and do other things like fetch me the first node. I can set a specific attribute on my node if I wanted to. So doing this operation means that your data is reflected in Arango. So if we go to our collection, we can see over here that indeed we have the contents of foo bar added. I can, of course, delete the node or delete this attribute if I wanted to, go back to my DB, refresh my page, and then the attribute goes away, right? So you can apply this to adding an extra node, for example. So if we add a node 35 with a parameter, we can do the same thing for adding an edge. So we can say add an edge from node 1 to 35, and let's set the weight to, for example, 3 or 4. If I go back to my DB, go to my collections, go to the end of my collection for nodes, I can see my 35th node has been added, along with my 79th edge, which has been added all the way at the end over here. Right, so this is just another example. Let's do some basic algorithm stuff. So if I just give us more room for code and scroll down, let's run a quick algorithm. We'll just invoke PageRank over here on the NetworkX graph, and then we'll iterate through the results of the PageRank, and then we'll simply persist those results back to the individual nodes of my graph. So from here, if I just quickly go back to my nodes and go back to my data, I could see here that, okay, I've got now PageRank associated to node 6. And then if I go to, for example, my nodes here, I can say, all right, well, here's what we'll do. Oh, looks like I used the wrong graph, but it's the same thing. If I switch over to the ArangoDB graph, it'll iterate through the ArangoDB nodes and then insert the PageRank value. So if we go again, here we go, we've got PageRank listed everywhere. If I say something like gadb.chat, I can also leverage some LLM capabilities here. So if I don't feel like using the traditional views that NetworkX offers, I can just rely on LLMs to do this for me. So something as simple as, I don't know, fetch me the node with the highest PageRank. We'll set this option to true as verbose. And then here you'll see that we're entering a LangChain, the LangChain integration, which we have, which will translate the natural language request into AQL. And so, of course, the nice thing for NetworkX users is this is all new, right? So because your data is now in Arango, you can leverage the AQL and thereby allowing you to leverage natural language. Something more sophisticated, for instance, we could say, I don't know, gadb.chat. Let's just say, take this statement and let's just make it a bit more complex. From that person, fetch me all other connected let's say connected persons. For each connected person, update each document to add an attribute foo with value bar. And we'll set that verbose to true so that you guys can see what that looks like, see what we get in terms of query. And so the nice thing about this is you're using LangChain, which means that it's model agnostic, right? Right now, this is just, I believe, using GPT-4, but you're free to do this with whatever model you decide. So now if I go back to, for example, my database after this operation, just to validate it, I can just go back over here. I can see now nodes, specifically speaking, the nodes related to the highest node, the node with the highest page rank, which is 33. All nodes linked to node 33 now has the attribute foobar, right? So this natural language interface gives you a place to read data, but also modify data if needed.
We have a question around the dynamic nature of this, and certainly the performance as well. The performance is inherited to or accrues to the ArangoDB platform, where there's billions of nodes and edges, right? We've scaled that, and on the document level too. But what you're showing us is the dynamic nature of this, where a user can ask any question after some basic model training and prompt engineering, right? You don't have to go and write AQL. That's the beauty of it. It's dynamic, correct?
Exactly. Yeah. So you don't need to learn a new query language to use our tool. You can just rely on natural language if you don't feel like adopting AQL. Yep. Cool. All right. So let me continue. I'll switch over to the GPU portion now. So we're going to switch databases. I've already got a data set, loaded into my database. It's called citation patterns. And this data set is similar, or actually it's identical to the one that Rick was recently talking about. It's from Snap, and it's a representation of different citations across, I think, let me just quickly double check. Granted, yeah, between 1975 and 1999, a bunch of citation patents, and it has about 3.7 million nodes and let's go to this collection, 16.5 million edges. And so what we're going to do is we're going to invoke betweenness centrality on this data set. Let's say, for example, we're interested in finding patents that are more central than others to get an idea of their relative importance. So exact same setup. I'm just going to instantiate a NetworkX ArangoDB graph. This time, however, since the graph already a data set, I only need to provide the actual, just the name of that graph. So it's called citation patents. I'm going to specify my database connection object. And so it says here that it found the graph and the default type has been set to nodes, which is great. If I print the graph, I can get confirmation of the size. And then from here, I can invoke my first algorithm. So going back to that slide that showcased some of the dispatching architecture that we offer, this is where we see dispatching going to the GPU implementation of the algorithm we're running. So in this particular case, I'm requesting to run betweenness centrality with a K value set to 10. And it will basically take the data in ArangoDB and fetch the COO representation of that graph instead of fetching the CPU representation, which is the adjacency view and the node view. This means that you're, one, taking less memory to fetch the representation, and two, it's going to be way faster when you run your betweenness centrality algorithm. So we can see here that in this particular case, loading the data, the graph data from ArangoDB into memory on this Jupyter Notebook machine took around 20 seconds. And then the remaining 6 seconds was the time it took to run the algorithm in question, right? And I can confirm that by running a second algorithm. So if I say PageRank result equal nx.pagerank and provide the graph, in this particular case, because the graph is already cached locally, it's only going to spend time on running the actual algorithm. Let me just put the time decorator just to confirm. So there's no instance of loading the data. It's already cached in memory, right? So this is one particular benefit of working close to your ArangoDB deployment. These Jupyter Notebooks, they sit right next to every ArangoDB instance. It's running in the same Kubernetes cluster, which means that read and write capabilities are significantly enhanced, allowing you to get numbers like this on a deployment that only costs $2 an hour to run, right? So of course you can expect for billions of nodes and edges, if you scale this up, you can assume the same kind of performance when relative to the data set, of course. And so this kind of just showcases overview of where we stand from a QGraph perspective. Now, to Rick's point earlier about caching, the graph is cached right now, and it's only relevant if you don't do any more read or writes, right? So we're working on this functionality where you say, okay, at this point, if I were to add an edge, from node 1000 to node 2000, I want that cache reflected for my QGraph graph so that I don't need to take the hit again on loading. And so if it's even preferred, you can opt as well to just convert the graph at the front instead of having it done in the background for every algorithm call. There's a function hidden within the NetworkX ArangoDB package that allows you to say, okay, take my ArangoDB graph, convert it to a QGraph graph, and then you can pretty much do whatever you want with this graph once you have it in memory. So this kind of overall gives a quick overview of where we're at. Hopefully that was fast enough. And yeah, Corey, this is pretty much a quick demo of where we're at. If you're interested, the repo is just on GitHub. Just look up NX ArangoDB, and you'll be able to find it pretty easily.
And Anthony, for folks that want to get started with the Arango, it's easy.
Yeah, for sure. So you've got a few options. Now, the easiest option I would say is to spin it locally. But if you're interested in a more enterprise and you want access to production ready persistence, then I would recommend you start with Arango Graph. There is a 14-day trial set up. So if you just go to dashboard.arangodb.cloud, you can sign up, and from here you're good to go. Additionally, we have Docker images available for ArangoDB. So if you're interested in that, easiest two ways to get started.
And when we say Arango Graph, we're talking about our cloud-hosted managed service, which is so easy to get started with. And maybe you can show the connection to where that connection is specified, or you may have shown that at the beginning, but
Yeah.
what would that look like with Arango Graph? Just so
Yes.
people know when you set that up, what can you then do right away there?
Yeah, just double checking, is the person referring to the connection credentials to get started with the NetworkX ArangoDB backend?
Well, that was my question.
Yes, got it. So
which is how they can get connected to Arango Graph once they sign up, which is, even also from our website, just click on free trial.
got it. Exactly. Yeah. So it's just a matter of clicking the start free button over here. You can sign in with some SSO, and then, you're redirected to basically some information about you, and then, yeah, you're good to go. The NetworkX perspective, it's just a matter of specifying the host, the username, and the password, along with the database. And, all of this can be grabbed from your Arango Graph dashboard. So you'll have access to something similar to this, with your endpoint, your password, and then the username, which you can use root, for example.
Yeah, looking into the chat and the Q&A, looks like there's a lot of interest in the right there, the way you can quickly use LangChain and implement. And that really is the benefit, folks, is that you can really quickly add natural language. Once you persist to Arango, you can add a natural language. You can build applications there with that persisted data, and then add and build those applications. So maybe you could speak quickly about any model training or prompt engineering that goes into this real quick to get this going.
Yeah, for sure. So right now, what you're seeing is a LangChain setup that we have in an ArangoDB setup we have in LangChain. So if you just quickly look up ArangoDB LangChain, you'll see that we have a QA chain supported in ArangoDB, allowing you to provide natural language interface to Arango. Now, in terms of model training, there is actually none here. What we're relying on is simple prompt engineering to set up a set of instructions for the LLM model to say, take the responsibility of converting the user's prompt into AQL, execute the AQL in the DB, and if there is an error that comes back, fix it, and otherwise keep trying until it successfully executes, and then translate the JSON result back to natural language. We do provide techniques for additional prompt engineering or additional, if you want to call it few-shot learning. If you'd like to expose that, it's possible by just, and we've got that instruction in the documentation, but essentially you could say, if you want your LLM to cater to a certain way of writing AQL, there is a way of saying, okay, well, I'm going to provide a set of examples that basically provide a natural language prompt and then provides an opportunity for the LLM to learn from your AQL queries, right? So that's possible. But personally, we've seen very good results from just prompt engineering and just relying on whatever knowledge that the LLM knows about AQL. Not to say that fine-tuning is also possible.
In the minutes we have left, please provide your questions. I do want to open it back up at the last few minutes to Rick and Brad on their final comments about what they see for the future. But there is a question here: would this work with libraries that build on top of NetworkX as well? Maybe Brad or Rick, you could field that one.
I was saying everything we are doing is hidden under NetworkX. So if your application leverages NetworkX, it just magically gains access to all this, including, persistence, acceleration, everything. Rick, were you going to add other to that?
No, basically the same thing. The whole goal here was zero code change acceleration, which sort of implies then any application written on top of NetworkX, once you enable those various backends, they will see those benefits. So that's a use case we're really looking forward to seeing more as this kind of propagates further out into the community.
This also allows you to have much larger graphs than you could typically with NetworkX. And you don't have to always pay the price of updating it and reloading it every time.
By the way, Anthony, incredible demo. You're a great demo guy. I love making videos with you. If you go to YouTube, our YouTube channel, you'll see some videos. One of the questions was on vector stores with RAG, and there's a great paper that BlackRock and Nvidia published, if you do a quick search on that, on hybrid RAG, which is how you can use graph RAG and vector RAG together, which was such a great paper, I thought. Certainly, right, one versus the other are good in different ways, right? With vector RAG, it's the semantic comparison or meaning, right, Anthony? And with graph RAG, it's more around the specific context and the right? Is that how you would differentiate it?
Yeah, and I mean, recently speaking as well, the approach of using both it can combine in a hybrid fashion is also of interest. So yeah, stay tuned for more of that stuff coming soon.
I was going to say there's a great question out there that I was saving to the end is, can you use it to build recommendation systems? And I did not just want to type yes as an answer, so wanted to see if Anthony had more to add to that.
Yeah, so I mean, we've certainly seen customers at ArangoDB use this database for building recommendation, platforms. So the short answer is yes. Without knowing a bit more about what you're interested in doing, I can't say like what you'd like, but I mean, feel free to reach out to us and we'd be happy to help.
Yeah, as I said earlier, the recommendation piece is really also powered by our GraphML solution, which will, and if you have an interest in that, we can set up a call to talk through how that works. But that is where the power, right, Michael? Are you on the call? You want to chat quickly about that in the 2 minutes left?
Yeah. So absolutely. So using GraphML, we can actually try and train a model that helps you with the recommendation systems. Let me quickly sort the use cases in my head.
No, I just want to mention I did completely forget to bring up that, the notebook interface we were working on, gives you access to more than just the Python package management that we saw today. It gives you access to being able to run and use our machine learning services. So we've got things like as for node similarity or node classification, all embedded within the Jupyter Notebook, so that you can provision machine learning jobs such as featurizing your data or training machine learning models or applying inference, all through this Jupyter Notebook. So that's just a small side note. This is more than just using analytics. It's really for machine learning as well.
All right. Well, we're close to the end here. If there are any points about what you'd like to see in maybe the next version of this, we certainly can entertain those things. But I will. Oh, here's a question. What will the best approach be for the GPU-driven performance test on heavy workload?
So again, we are kind of hiding the fact that GPUs are in the background. So there really is not like a best approach. You just type your algorithm and then, under the covers, we'll figure out the best way to leverage GPUs or CPUs or whatever is out there. We are constantly updating our algorithms and making them better. And also that just magically shows up as better performance for you.
I saw these numbers earlier, but we're seeing hundreds of times faster with GPU versus CPU using this platform. Is that right?
That is correct. Once we get over 100x faster, it starts becoming meaningless because some algorithms, I think we have been like 7,000x. And so, the NetworkX folks realized that their implementations are not the best. They were all single threaded, written 15 years ago. So there are other efforts to improve the algorithms in NetworkX. We are just giving them alternatives. Again, though, it's all under one API, and the user just says run between this, and they get the best performance based on the system.
Yeah, that's really the key. These backends enable NetworkX users to stay in NetworkX and still scale their workloads. For the question, the best approach for a GPU-driven performance test on a heavy workload, I guess it depends on what your comfort level is. If you like staying in NetworkX and like all the advantages that tying in with NX ArangoDB and cuGraph is, then certainly you can stay there. If kind of like the slide I showed, where the further down the stack you go, the closer to CUDA you get, you can see improved performance benefits. You can always rewrite sections of your code to be a little more optimized, eliminate some of those conversion costs that we do for convenience, and go that way. I think that answers the question somewhat. Trying to make sure I understood though.
Well, listen, folks, this has been a great session. I want to thank our guests from NVIDIA and Anthony again. Wonderful demo. And we will have this recorded and available to all of you and anybody that missed today's event. So with that, we're going to wrap up, say thank you, and we will see you all on the next ArangoDB and hopefully with our guests NVIDIA as well. Take care, everyone.